Hello everyone, myself Nupur Mittal. I am the faculty of EN department from Ajay Kumar Garg Engineering College. Today in this lecture, I am going to start the left out part of the signal flow graph. So these are the basic contents of today's lecture. Here I will discuss about how to convert the block diagram into a signal flow graph, right? And then we'll move to the Masson-Gain formula and we'll discuss some examples based on these two topics. In the previous lecture, I have defined the signal flow graph, what is the need of signal flow graph and why we require the signal flow graph, right? What are the basic steps to design the signal flow graph? Then what are the terminologies used in the signal flow graph? But the two topics, there are basically two methods to convert any particular network into a signal flow graph. First one is by using the equations that I have discussed already. Now, the second one is the method of conversion of block diagram into signal flow graph. So, we'll discuss this method in this lecture and then we'll discuss about the Masson-Gain formula. At last, we'll discuss some example on both these topics. So, let's start with the conversion of block diagram into signal flow graph. So, what are the steps how to convert the block diagram into signal flow graph? So, first step is we have to represent all the variables, all the summing points and all the takeoff points of the block diagram into the nodes of signal flow graph, right? Represent all the variables, summing point and takeoff points into as nodes of the signal flow graph. Then second point to be kept in mind is we have to represent all the blocks with the branches, right? Blocks of block diagram can be represented by the branches in a signal flow graph. Now, third point is we have to represent the transfer function which is inside the block of the block diagram by the gains of the branches in case of signal flow graph. Okay. And at last, we have to connect all these nodes of the nodes accordingly. If there is a connection in between the two, if there, let's say there is a connection between two nodes, right? So, we have to represent the gain of that particular node by unity, that is 1. For example, we have two summing points. Let's say we have these two summing points, right? So, this is summing point number 1, let's say this is number 2. So, this is for the case of block diagram, right? When we convert it into the signal flow graph, then we will represent these two summing points with the two nodes, right? With the two nodes, 1 and 2. First node number 1 for the summing point 1 and node number 2 for the summing point 2. Now, you can see here no transfer function is represented between these two summing points. So, we will connect these nodes and represent 1 as the gain of this particular branch. Okay. Similarly, same is the case with respect to when there is a summing point along with the takeoff point. When a summing point is connected with some takeoff point is there just after this summing point, then in that case, we have to represent these two with different two nodes. One is for this summing point and another node is for this takeoff point. So, in this case, again, between these two nodes, we will connect a branch and represent the gain as unity, since there is no transfer function is represented here in this case. Okay. Same is the case between the takeoff point and the output, and between the input and with summing point or with some takeoff point. We will take gain as unity. So, let's take an example here. You can see we have to convert this particular block diagram into the signal flow graph. So, first of all, we have to represent all the blocks, all the summing points and all the takeoff points by the nodes. So, here you can see we have RS is the input, CS is, YS is the output here. Okay. So, you can see one summing point, this is 2, 1, 2, 3 and 4. There are 4 summing point in this block diagram, right? Then we can see 1, 2, 3 and 4. There are 4 takeoff point in this block diagram, right? And you can see in between these two blocks, right? In these, between these two blocks, we can consider one node here, okay, between these two blocks. So one node will be for these two blocks. So there are total 9 nodes. So for this, except these 9 nodes are excluding the RS and YS, input and output, okay? And the gain between G1 and G2 block will be represented by 1, okay? So here you can see this is the block diagram. Now let's try to make the signal flow graph. So for this particular, you can see I have represented the nodes by Y1, Y2, Y3, Y4, Y5, Y6, Y7, Y8 and till Y9. Okay. So there are total, these are the actually the name of the nodes. Okay. So we have started with this RS. One is the node that is YS. Okay. And then node number Y1, Y2, Y3. Now you can see between Y1 and Y2, there is no gain. Okay, no transfer function. So we will represent it by gain, that is unity. So you can see between Y1 and Y2, there is a unity gain, right? Similarly, you can see between the node RS and Y1, there is no gain, though no transfer function is represented. So we can represent it by unity. Okay. Now between Y2 and Y3, see this is Y3. So between Y2 and Y3, there is a block, that is G1. So we will represent the gain of this particular branch which is connected between Y2 and Y3 by G1. Similarly, you can see Y3 and Y4. Y3 and Y4, we have a block which is having a gain of G2. So the node, so the branch between Y3 and Y4 will have the gain of G2. Similarly, now between Y4 and Y5, again there is no gain. So we will represent it by 1. Okay. Between Y5 and Y6, there is no gain. We will represent again it by unity. Now Y6 and Y7, we have, see, we have 2 gains in between Y6 and Y7. Both are in the forward direction. One gain is G3. Okay. One branch. So we will make 2 branches between Y6 and Y7. Okay. We can make 2 branches. This is Y6 and Y7. The first branch will connect these two like this, and it is being shown by the gain G3, okay, because of this block, right? Now the second node, second branch will be shown by this G4. So we can connect another branch between Y3, Y6 and Y7, and we will represent it with G4 gain, okay? And the direction will be taken from here. You can see the arrow is showing the direction here. So between Y6 and Y7, we have 2 branches and there are 2 different gains between Y6 and Y7. Now between Y7 and Y8, again there is no transfer function or any gain is representing here. So we will take it as unity. You can see between Y6 and Y7, we have taken 2 branches. Okay. Then coming to Y7 and Y8, it is again unity. Now Y8 to Y9, it is G5. So between Y8 and Y9, it is G5. And then Y9 to YS, it is again 1. Now, I have left these 1, 2 and 3. Now see, this H1 is connected between node Y4 and between node Y2. And you can see the direction, it is the reverse direction. Okay, feedback direction with a negative sign. So between Y2 and between Y4, I have connected here H1, which is having a negative sign here because of this negative sign. It is in the direction of feedback, right? Similarly, between Y8 and Y1, there is a block that is represented by the transfer function H2 and it is having a positive sign. So there is a feedback block. We will connect between Y8 and Y1 with a transfer function with the gain representing H2. And one more H3 is between Y9 and Y5. And again, it is a feedback, okay, with a negative sign. So between Y5 and Y9, I have connected this branch with a negative sign, okay, and it is having a gain of minus H3. So hope it is all clear to you. So there are total 9 nodes along with the 2 nodes, external nodes, for one for the input and one for the output. And we can connect, so in this way, we can convert the block diagram into the signal flow graph. Now coming to the Masson gain formula. So see, S.J. Masson have introduced the concept of the signal flow graph so that we can simplify the circuit we can analyze the circuit in an easier manner. Okay, so basically this is a technique to find out the transfer function of any particular system, right? And the formula which determines the transfer function of any linear system by making use of the signal flow graph, that is known as the Masson gain formula. So this is the Masson gain formula here. Let us say we have n forward paths in any signal flow graph. So the gain between input and the output nodes of the signal flow graph is nothing but the transfer function that I have already shown you in the previous slide also. So we can calculate the Masson gain formula by this formula. So you can see here T is the transfer function. Okay, Cs is the output of that system, Rs is the applied input to that system, and this is the formula which is representing summation I is equals to 1 to n Pi into delta I upon delta, where this Pi is the forward path gain and this I is representing the number of forward paths. Okay, delta I is basically, see, Pi is the forward path gain and delta is basically 1 minus the sum of all the individual loops, okay, plus sum of product of possible two non-touching loops minus possible sum of gain products of all 3 non-touching loops plus sum of gain of product of 4 non-touching loops and so on. See, the sign minus, it start with minus sign and it is an alternate sign, minus then plus then minus then plus, and it start with the individual loop gains, okay, then 2 non-touching loops, then 3 non-touching loops, then 4 non-touching loops, whatever be possible, we can go till that. Okay, and here delta I, it is obtained from delta only, okay, by removing the number of loops which are touching to that particular path. Okay, delta I is representing the basically the loops, the value which is obtained by removing obtained from delta by removing the loops which are touching to that particular path. See, this is the example here. We have to find out the transfer function for this Masson gain by using for the signal flow graph by using the Masson gain formula. So here you can see, I have already discussed in the previous lecture that how to find out the forward path, how to make loop. Once again I am revising here. See, you can see the number of loops in this case is 1, 2, 3, 4, 5. You know, this is one of the loop which is in between, which is having a gain B, forward path gain as B and reverse path gain as J. Okay, it is between these two nodes. Okay, here the name of the nodes, okay, Y2 and Y3. It is between Y2 and Y3. Okay, similarly there is another loop between Y4 and Y5 which is this one. Forward path gain as D and reverse path gain as I. It is between Y4 and Y5, right? So this is the loop. I have told you that the feedback loop is a loop which is started from a particular node, traces at least, travel to at least another node and then terminated at that particular node only. So these are the loops here, and I have already told you there is one self loop in this case. You can see this is the self loop which is started at the same node Y5, okay. It is having a gain of E. This is the self loop, that is Y5, which is having a gain of F. Self loop started from a node, it does not travel to another node and terminated to that particular node. Right. So here in this case, we have this one loop, 2, 3, then another loop will be between Y3 and Y5. We can travel from Y3 to Y4, then Y5 and then back to Y3. So you can see this is the loop between Y3 to Y5, Y3, it is node Y4, then it is y5, okay, and it is having a gain that is C, D and H, okay. This is the another loop. Now the last loop formed here will be, that means total 5 loops are formed in this particular signal flow graph. The last loop will be started from y3 going to y5 and then coming back to y3. You can see this is the last loop. It is started from y3, it will go to y5 and then coming back to y3. So y3 to y5 G is the gain, and from y5 to y3 H is again the gain. So there are total 5 loops for this particular signal flow graph, and the let's talk about first the number of forward paths, okay. So you can see one is the forward path when we move from y1 to y2, y3, then 4 to 5. This is one of the forward path, okay, from y1 to y6. Another forward path could be from y1 to y2, then y3, and then directly to y5 to y6. So another forward path could be, this. It is y3, then it is y5. It started from y1 and it ends to y6, okay, including the node y2 here again, and y5, y6, okay, y1, y2, y3, y5 and y6, okay. This could be the another forward path. So you can see the total number of forward path here is 2. One is this y1 to y6 that I have shown here, and another one, it is this path is having a gain of, I have already told you how to get the gain of a particular path. Just multiply the gain of all the branches which are included in that particular path. So the gain of this path will be A into B into C into D into E, okay. Then another path will be y1, then y2, then y3, y5 and then y6. This is the second path, okay. And again the gain will be path gain will get multiplied all the branches individual gain and will get the combined path gain. So it will be A into B into G into E. This is the, and I have already discussed all this. There are total 5 loops in this figure. These are the 5 loops. Gain for this path will be, loop will be F only, right? Gain for this loop will be G into H. Gain for this loop will be B into J. We have to simply multiply the gain of the forward path and the gain of the feedback path for a particular loop, okay. For this it will be C, D into H, okay. So these are the loops I have already discussed. These are the total 5 loops and these are the gains, okay. So now to see how many loops are not touching to each other, we have to take into consideration the 2 non-touching loops and 3 non-touching loops here, and then we'll move further. If there could be a 3 non-touching loop, then we'll see for the 4 non-touching loop. But if there 3 non-touching loops are not existing, then there is no need to see for the 4 non-touching loops. So you can see from this figure, you can see this loop. Let's say this one which is started from y2, y3, and this loop is not touching this loop. So these are the 2 non-touching loop in this case. Similarly, this loop is not touching this self loop. So one combination will be this one, okay, that is this one, yes, y3 to y2, y2 to y3, then y2, and then this y4 to y5, then back to this. Another combination will be this into self loop, okay. The gain is that in this. Second will be self loop ke saath this wala loop, this loop. The combination, the loop gain will be this. And there will be no other loop is only there are 2 non-touching loop, because with this particular loop is having this node in common. So we cannot, and similarly for this loop, this particular loop is having this node in common. Similarly for this particular self loop, this node is in common. So there are only 2 combinations. So there are only 2 non-touching loops. And there is no possible combination for 3 non-touching loops. So now let's put all this value into the formula for Masson gain formula. And for that we have to first find out the value of delta. That is 1 minus sum of all individual loop gains. I have already calculated at the previous slide the individual loop gains. This is the individual loop gains, and then plus sum of gain product of two non-touching loops, right? So these is the sum of the gain product of two non-touching loops. Since there is no three non-touching loop, then we'll put minus 0 here, and the total value of delta will get this. Okay. Now we have to find out the value of delta 1 and delta 2. So you can see delta 1 was the forward path, this was the, है ना, and you can see all the loops are touching in this particular forward path. So the value of delta 1 will be 1, because we have to find out the value of delta 1 from the delta only, but the value will be 1 minus the individual loop which is not touching to this first path, okay, and plus sum of the products of those non-touching loops which are not touching to this particular path, that is first path which we are talking about here. So this value is 0 because all the loops are, individual loops are touching this forward path. Again this value is also 0. So we have got delta 1 is equals to 1. Similarly for the delta 2, you can see for delta 2 the value will be 1 because this is the second path and all the loops are touching these. All the loops are touching, all the nodes are common in between the forward path, second forward path, and the feedback loops or the self loop. So the value of delta 2 here is again 1. Okay. Now we put the value here. Pi delta I means there are since 2 total paths. So I will goes from, started from 1 and will goes to 2. Now transfer function will be P1 into delta 1 plus P2 into delta 2 upon delta, and we'll put the value of forward path gain first 1 into 1 delta 1, B2 is this and delta 2 is this, and we'll put the value of delta which we have calculated in the previous slide. So finally after solving these values, we'll get the value of transfer function as ABCDE plus ABGE upon 1 minus BJ plus GH plus CDH plus DI plus F plus BJ DI plus BGF. And so this will be the value of the transfer function for this particular signal flow graph. And we can further simplify if there is any possibility. Okay. Now this is another example for the Mason gain. Again for the signal flow graph, we have to find out the transfer function using this Mason gain formula. See here in this case, you can see we have only one forward path. Since it is a feedback path, it is again a feedback path, here also feedback path, and here also we are having a feedback path. So here in this case, we are having only this forward path from RS to CS. Okay. So there will be how many nodes? 1, 2, 3, 4, 5, 6 nodes excluding the input and output node. Okay. So forward path will be the forward path gain will be the multiplication of all the individual branches gain, okay, which are included in this path. So it will be 1 into G1 into G2 into G3, 4 into G5 into 1. So this will be the gain of the forward path. So here the value of I, or you can say K, will be 1, right? Now let us see how many individual loops are formed here. The first loop will be G1 into minus H1, okay. The second loop will be G2 into minus H2. Okay. The third loop will be G4 into minus H3. And the fourth loop will be, it will be G4, G5 and minus H4. Okay. These are the 4 loops formed here in this case. These are the 4 individual loops. So you can see these are the, these are the 4 individual loops L1, L2, L3 and L2. For this loop, the gain will be minus G1 into H1. See, you can see L1. For L2, gain will be G2 minus H2. Sorry, minus G2 into minus H2. Okay. So it will be minus G2 H2. Here for this G4 into minus H3. So this will be minus G4 H3. Similarly, for this G4 into G5 into minus H4. So the loop gain will be minus G4 into G5 into H4. Now let us see the 2 non-touching loop. You can see for this particular loop L1, this is also a non-touching loop. These 2 loops are not touching each other. So one combination is this. Similarly, this loop, the bigger one, this one and this one are not touching each other. This one and this one are not touching. So this is another combination. So let's say this is L1 and L3, one combination. L1 and L4 will be the another combination. And we can see similarly for this loop, L2 is not touching the L3. Similarly, L2 is also not touching the L4. So this is the another combination. And we can get the gains will after multiplying the gains of the individual loop. So this will be the gain of the two non-touching loop. Okay, and there is no possibility for three non-touching loop. See this, and if we talk about this and this, but this is having a common node, these two loops are having a common node. This, if we talk about this one and these two, these are having this common node. So the three non-touching loop gain will be 0. Okay, so here again the value will be for the transfer function. Here the value of transfer function will be only T1 into delta 1 upon delta, right? Now delta 1, let's first define the value of the delta. So delta will be 1 minus the gain of L1 plus gain of L2 plus gain of L3 plus gain of L4 within a bracket, and after bracket again a minus sign and summation of these four combination. You can see here delta will be 1 minus L1, L2 plus L3 plus L4, then plus sign and the combination, all these four combinations, right? So the value of delta will be this. Now the value of delta 1 will be 1 minus those loops which are not touching to this individual loop. So you can see all these loops are on this path. All the loops are having a common node with this forward path. So the value of individual loop gain will be 0 in case of delta 1, and will get the value of delta 1 as 1 only. Okay, so we can write this transfer function. Now we can put the values of the gains in this formula and we'll get the value of the transfer function as this. That is, the transfer function will be G1 into G2 into G3 into G4 into G5 into 1, okay, upon the value of this delta. That is 1 plus G1H1 plus G2H2 plus G4H3 plus G4 G5 into H4 plus G1 G4 H1 H3 plus G1 G4 G5 into H1 H4 plus G2 G4 H2 into H3 and plus G2 G4 G5 H2 into H5. So this is the value of the transfer function for this particular signal flow graph. Okay, that's all for today's lecture. I hope this signal flow graph is clear to you, and thank you so much.